Non-planarity of Peterson graph. So now we are going to check whether this Peterson graph is planar or non-planar based on the learning. What we have as of now is any graph which is supergraph of subdivision of K33 and K5 is non-planar. Okay, let's do one thing. Let's try to figure out whether this particular graph contains K5 or K33, subdivision of K5 or K33. Okay, so let's start with that. First, the graph will not be a subdivision of K5. The particular reason behind this is, see, K5 is basically a complete graph of 5 vertex. Now all the vertex has degree 4 in K5, but in the Peterson graph what we can see, every vertex has degree 3, so we cannot find out any subdivision of K5 in this graph. But we need to check if it is a subdivision of K33, because the complete bipartite graph of 6 vertex is also having the degree 3 for each and every vertex. Now here in Peterson graph we are also seeing that every vertex is having degree 3. Now this is a probable candidate and we need to check whether we have a subdivision inside this Peterson graph. We have a subdivision of K33 inside this Peterson graph or not. Okay, so let's start with this procedure. So first let's pick a vertex of degree at least 3. Okay, so let the vertex be H1. So we have marked that particular vertex H1 and it has degree 3. Since K33 has degree 3 for each and every vertex, so we have chosen one vertex H1 with degree 3. Now find the 3 other vertices of degree at least 3 from which there is an edge to the vertex H1. Okay, so yes, we are seeing there is 3 other vertices of degree 3 which can be reached from H1. So let the vertices are U1, U2 and U3. So we have marked it through the red color. The edges between H1 to H1 and H1 to U1, U2 and U3 is marked in red color. Okay, so let's proceed. Pick the second vertex of degree at least 3 and let the vertex is H2. So we are seeing a lot of other vertices are there which has basically the degree 3. So we have chosen a vertex from that list. So let's say we have marked this as a vertex H2 and we have colored it in blue. Okay, now connect H2 to U1, U2 and U3, and these paths should be disjoint from the previously selected 3 paths from H1. So basically we are trying to find out the K33 bipartite graph. So every bipartite graph is basically have 2 groups of vertices. So we have marked one group of vertices as U1, U2, U3, and we are marking the other set of vertex which is H1, H2 and H3. So these are 2 different groups. So we have marked another vertex H2 which comes in the same group of H1, and since these H2 should have edges to U1, U2 and U3, so we need to find out the path from H2 to U1, U2 and U3. But while doing so, we need to remember one thing, that we should not consider the edges or paths which we have already considered. okay, in the previous previous slide. Now, so let's find out three different paths to H1, U1, U2 and H3. So I have marked it in the green color. So now I have H1 and H2, and these two vertices are basically having degree as 3 and connected to U1, U2, U3 by 6 different paths. Okay, now the we need another vertex. So let's find out another vertex having degree 3, and we marked it, let's say, with H3. So we have marked it in blue, and let's say the vertex is H3. Now we need to find out the path from H3 to U1, U2 and U3. And while finding out that path, we need to remember this path should be different than the previous 6 paths which we have already selected. Okay, so we have again found out the paths from H3 to U1, U2 and U3, and I have colored it in blue to identify separately. So what I have got it, we finally found something, H1, H2 and H3. Okay, so this is one group of vertices, and U1, U2, U3 is another group of vertices, and probably we are going towards K33. We are actually we will be able to find that K33 within few minutes. Okay, so now we need to check what are the remaining edges which is not actually not the part of K33. So there are yellow edges which is not part of K33. So let's remove all the yellow edges. Okay, so let's remove those yellow edges. Now after removing those yellow edges, we need to do one thing: remove all the vertices not colored which are responsible for subdivision. So we are seeing quite a few vertices which is not colored. Those particular vertices are basically responsible for the subdivision process. As we have already shown that we can always delete. If we delete those subdivision vertices, then it will never add any new edge crossing. So we will delete them one after another. So we are deleting it and we are connecting them and we are redrawing it. Finally we get that K33 graph. So what we found is the Peterson graph has basically Peterson graph is basically the superset of the subdivision of K33. So we can conclude the Peterson graph reduced to K33, which is non-planar, and from this we can conclude that Peterson graph is also non-planar. Okay, so we have learned how to check the planarity of a graph using the using the topological concept. So we will try to find out if any graph given to us. First we will try to find out whether it contains a subdivision of K33 or K5. If we get it, then we will say this is a non-planar graph. If we don't get anything of that sort, then we will conclude that it's a planar graph. Now this is little tedious. Every time we need to check. There are lots of algorithm to find out all those things. We are not discussing those topics in this lecture, but conceptually we found a way how to say one graph is planar or non-planar. Now let's see some characterization of planar graphs and Euler's formula. When a planar graph G is drawn in the plane without edge crossing, it cuts the plane into regions called faces of the graph G. The set of all faces of G is denoted by capital F and the number of faces by small r. So the total number of element in capital F is basically r. So we have given two different examples where r equals to 1 and r equals to 2. So one face graph, r equals to 1 means we have only one face. So obviously it is a tree, and the r equals to 2 is another graph which has two faces, one is interior and another one is exterior. Now, so we have a question like how many faces are there in the following planar graph? So it appears to be 5 at the first glance, f1, f2, f3, f4 and f5. But if we redraw the graph in a different way, means if we create a plane graph from the previous graph and if we remove the edge crossing concepts, then we will have only 4 regions, 4 faces, f1, f2, f3 and f4. Okay, so that means the counting of face, when the question is we need to count the faces of the graph, we need to draw it in the plane, right? Even though it's a planar graph, there is no guarantee that a planar graph, we can always draw the planar graph in such a way that we can avoid the edge crossing. Okay, so when we want to count the faces, then we need to make the planar graph to plane graph. That means we need to draw the graph in a without edge crossing. So after that only we can count. So if we have a different orientation and if there is no edge crossing, still the count remains the same 4, right? So the correct answer is 4. So the face is only defined in connection with crossing free drawings of the planar graph. So before we start counting the face, first we need to make the graph a crossing free drawings. Okay, so then only we can count them. Okay, so in this particular question, the total number of faces equals to 4, not 5. Except one phase, every other phase is a bounded region. That exceptional phase is called the exterior phase and other phases are called interior phase. The boundary of a phase F is the set of all edges of G which are incident with F. It is denoted by B of F, boundary of F. Okay. Now we have another definition, degree or size of a face. So degree or size of a face F in a plane graph G is the number of edges in the boundary of F with cut edges counted twice. It is denoted by DF. Now I will give an example and I will explain what is cut edges and what is what. Now we can also define degree in a little different way. Here we have defined degree we need to calculate how many number of edges inside the boundary, and if there is any cuttage we need to count it twice, and that count will give us the degree of or size of the face. Now there is another way to calculate degree. We need to visit the entire boundary with a boundary walk. So while visiting that boundary walk, the number of edges we will visit, that is the actually degree of that face. So we will come with an example. So this is a particular graph where we have so many vertices, 1, 2, 3, 4, 5, 6, 7 and so many faces also, f1, f2, f3, f4, etc. Now what we need to calculate is boundary of f1, and as per the definition of boundary of f1, we have found that 1, 2, 2, 3 and 1, 3 is actually the set, which is actually the edges which is actually inside a boundary f1. So boundary f1 contains 3 edges, and the degree of f1 is basically is the number of edges considering the cuttage as counting the cuttage as 2, counting the cuttage twice. Since in f1 there is no cuttage, so the degree of f1 is also 3. So the boundary of f1 comprised of 1, 2, 2, 3 and 1, 3, and degree of f1 is 3. So degree of f1 we can define it other way also, as we said. So if we start visiting the entire boundary, so starting from 1, we will first go to 1 to 2, 2 to 3 and 3 to 1. So the degree is 3 in that definition also. So this is degree. Now let's come to the face F2. Now this is little bit complex, right? So the boundary of F2, identifying the boundary of F2 is easier. Why? We need to find out the sets inside that, we need to find out the edges inside that boundary. So edges are simple, right? So 1, 2, 2, 3, so these are all edges. 1, 2, 2, 3, 1, 3, 3, 4, 4, 5, 5, 5, 5, 6 and 6, 7 and 7, 4. If you count these edges, we will have 9 edges. But if you look into that degree of F2, it's a mistake, it should be F2 instead of F1. If you see the degree of F2, it is 10, but the edge is 9. So we have defined the degree in two different ways, right? So one way is count all the edges. If any cuttage, then count twice. So here 3, 4 is the cuttage. What is cuttage? If you remove that particular edge 3, 4, then the entire graph will become a disconnected graph and it will have two different components, right? So we need to check whether any edge, if we remove that edge, if it is adding more component or if whether deletion of that particular edge is creating a disconnected graph, then we will say that it is a cuttage. So in this case 3, 4 is cuttage, so we need to count it twice. So this is one definition. And the another definition what we said, we need to start from one point and we need to visit the other points of other vertices of the face across the boundary. Okay, so if let's say for F2, if we start from 1, first we will go to 1 to 2, then 2, 3, 3, 4, 4, 5, 5, 5, it's a self loop, 5, 6, 6, 7, 7, 4 and 4, 3. So we are coming back, right? Since see here we are coming back. So 4, 3 is 3, 4 and 4, 3. The same edge is counted twice and then 3, 1. So again in that definition also dF2 is 10. Okay. Now if we see the final, if we see the third phase F3, there also we have edges 4, 5, 5, 6, 6, 7, 7, 4, 4, 8, 8, 9, 1, 2, 3, 4, 5, 6, total 6 edges. Now out of these 6 edges, 4, 8 and 8, 9, those are the cut edges. So we said cut edges needs to be counted twice, then therefore the total degree of this boundary having 6 phases is 8, because 4, 8 and 8, 9 is counted twice. And the final thing is the F4 phase. The boundary of F4 comprised of a single edge, that is actually self loop 5, 5, and the degree of that is also 1. Now we have few more remarks which is basically the consequence of Jordan curve theorem. The first one, a cyclic edge belongs to two faces. It's obvious, right? So we already said a closed Jordan will divide the entire region in three different parts, exterior, interior and the Jordan curve itself. So region, it divides two regions, right? The entire plane will be divided into two regions. So a cyclic edge, therefore a cyclic edge belongs to two faces. One is exterior, another one is interior. And a cut edge, and we have noticed, we have counted twice. For every cut edge, we have counted twice while calculating the degree. So a cut edge belongs to only one face, but while calculating the degree, we will actually counted it as twice. And the third remark is a plane graph G is acyclic if and only if the number of faces it has 1. So that we have already seen. Now let's have this theorem. If G is a planar graph, then summation of degree F, so sum of degree of all the faces is equals to 2 into m, where m is the number of edges. I need to prove this. Now the proof is very simple. So in a graph, the edges will be either a cyclic edge or it will be a cut edge. Now as per the remark 1, we know that every cyclic edge will contribute 2 to the calculation of the degree. And also we also found that every cut edge is actually counted twice while calculating the degree. So therefore, if we have total number of m edges in the graph, the total degree equals to twice into m. So we have written down that proof here. Every cyclic edge contributes 2 to the left hand side sum, since it belongs to two faces of G by the Jordan curve. Every cut edge also contributes 2, since it is counted twice, although it belongs to only one face. So therefore twice m equals to summation of the degree. Now let's have few more examples. So let's have a graph G. Now this graph has many vertices, edges and faces. So what we found, it has n equals to 6 vertices, v1 to v6, and m is 8 edges, e1 to e8, and r is basically 4 faces, f1, f2, f3, and the exterior region f4. Now if we check this formula, n minus m plus r, 6 minus 8 plus 4, this will give us 2. So we have observed for a plane graph, okay. So I am not saying planar because to count that faces we need to have a crossing free diagram, right? So rather, instead of planar graph, I will say plane graph. So every planar graph has a plane graph. So when I draw the planar graph in such a way that there is no edge crossing, it is known as plane graph. Since counting of face is very relevant when we do not have any edge crossing, so whenever we count r, the number of faces, we will say that graph is a plane graph instead of planar. So for this particular plane graph, we are seeing that n minus m plus r is equals to 2. If we take another example, which is again a plane graph, and it has 7 vertices and 12 edges and 7 faces, here also if we check that n minus m plus r, that remains 2 for this case also. So if you take any other plane graph and if you try to find out this expression n minus m plus r, you will always see the value is equals to 2, but only condition is that should be connected plane graph, okay.